Probably not. My degree plan only says I have to take college algebra.
107? Interesting, we might meet again. Now, this might tend to be a noisy room. We can certainly find a quiet room for you. Same for you? Okay, if you hang out near the window, it's a little quieter. Test bench. Boyd?
Hello.
Yeah,
Yes,
did make
Roshi?
it.
We took leave.
Yeah, we're on leave right now.
That's the same thing I had to do. I got it for today and next Wednesday.
You're on leave too?
Today, yeah.
We took Wednesday and next week.
Yeah.
Whole page.
Did you drive over? Who drives? You or Boyd?
He drives, because he doesn't wanna ride his scooter. Well, he wants to ride his scooter unless it's raining, so we usually use my car in carpool. Do you like teaching this class, sir?
I like teaching this.
This class?
This class, that 200? Yes, I do like teaching it because this is the course where you take the students the biggest distance, from here to there. Biggest distance in this course.
Everything else you use builds off of this.
Depends on your major. Psych? Yes, psych, we use it a lot. Psych.
Counting.
Maybe in your senior courses. Depends on which courses you pick. Some yes, some no. Yeah. But there are a lot of statistics in accounting.
And coming into this, I didn't realize that this course was so, like the exact precision on the numbers. But it's just kind of like, all right, around here, around there, we're within one or two here and there.
That is the way it is, just round here, round there.
And it's like I had, boy, my mind.
It's not exact here. No, not exact.
Never in a position where the numbers, the exact numbers didn't matter.
Oh, I see what you mean. They did matter. Well, you're an accounting major, so this course is sheer vomit for you. There's no question about it. We're loose here. Sorry about that.
I mean, my job is finance, so
You're
it's
right.
like
Yeah.
every penny counts.
It does.
Coming into this.
However, in this room, every minute counts. And if we spend 5 minutes getting everybody to have the exact answer, that's 5 minutes we can't teach concept. So it's a trade-off. Okay, now these workshops are student-driven, so if you don't ask a question, I sit here for 2 hours, so.
Okay. Well, I was waiting for you to say we're all systems go now.
Yeah.
We're all.
Can you crunch last class in 2 hours?
I could, but I just give you the video link, it's already recorded.
Okay,
So I'm still
sorry,
having-
you swap modes real quick.
It was a millisecond ahead of you there.
Yeah. go
You're
ahead.
first, sir.
I mean, hypothesis testing.
Got it?
That whole section, all of A12.
Got it.
I can understand how to get your H0, your H1. I understand your claim, anti-claim, null hypothesis, but that's as much concept as I can grasp out of this. I'm
Okay.
not understanding how, when I'm trying to plug these plug in this information and decide, to either reject or fail to reject.
Okay.
I'm not pulling anything.
Okay, I know exactly the problem, and I can speak to that. Did you want to go along with that for the moment?
Same, it's the same question.
Okay, since you guys know how to calculate, how to establish H0 and H1, so we'll start from there. And what you do after you establish H0 and H1 are two things. One, you establish a confidence level that you want your conclusion to have. 90 or 95% confidence. You have two possible conclusions are, now that you've formed the null hypothesis, you're going to perform a test. True? And take a sample. And there are two possible results to your test. One, you reject the null hypothesis as being true. That's clear what that means, right? You reject it. And you wrote it down yourself, what the null hypothesis was. Like P is equal to 0.5, or mu is equal to 4 pounds. Whatever it was you stated as the null hypothesis, and that's for the population now, by the way. That's for the population. But whatever it was that you stated, one result, possible result of your test is that you reject that as being true. You say, no, that's not true. With the amount of confidence that you've chosen. You say, I'm 95% confident that that's not true. Okay? Now, the other thing that you can do as a result of your test is you can fail to reject it. You say, it might be true, it might not be true. My test is not conclusive. I cannot tell. So I'm going to give it the benefit of the doubt, and I'm going to fail to reject it. But once again, I'm failing to reject it with only a 95% confidence. Maybe it's wrong. Maybe it should be rejected. But the result of my test is inconclusive. So what we're looking at is how do you decide whether the result of your test warrants you to reject the null hypothesis or warrants you to fail to reject it. And the key to that is realizing that your one sample is just one member of an infinite number of samples that could have been taken. And those infinite number of samples that could have been taken, and it's totally hypothetical because they're never taken, there's too many. But mathematically, if they could have been taken, that infinite set of samples would have formed a bell curve. And each data point in the bell curve would have a certain mean, just like your sample had a mean, agreed?
Okay.
They would be normally distributed. And not only that, but the center of them, and they will have a center because it's a normal distribution, agreed? This is the mean of all of the means that you could have taken. This is the mean of the means. And mathematically, it's also equal to the population mean. Now again, it's hypothetical, because we don't know what the population mean is, and we also don't know what the mean of the mean is, because to get it, we would have to take an infinite number of samples, which we're not doing. So now we're speaking hypothetically. Hypothetically, the mean of the means exists, because hypothetically, if we could take the infinite set of tests, then we could calculate it. So hypothetically, it exists, and mathematically, it's a bell-shaped curve, true?
Yes.
So since it's a bell-shaped curve, then 68% of the time, any sample that we take would be in that region, wouldn't it?
Yes.
That means that 68% of the time, any sample that we would take would be one standard deviation away from the center. And that's the result that we state. We state, as a result of our sample, we can state that the difference between the mean of the population and the mean of our sample is at most one standard deviation with 68% confidence, because 68% of the time, our sample would fall there, wouldn't it?
Okay.
So since it would fall there 68% of the time, then we can say 68% of the time, the mean of the population is with one standard deviation of our sample, true? Because 68% of all possible samples would fall there.
So my confidence level, 68% of the time, every sample I take will be within that one standard deviation. I'm
Yes.
68%
Right.
confident.
Right, and we just took one sample, and that was sufficient. So now we can say that there was a 68% chance that our one sample was within one standard deviation. But we don't have to stick with 68%. Now 68% has a partner, and 68%'s partner is one standard deviation, agreed?
Yes.
But 90% also has a partner. And what is the z-score for 90%?
1.645.
1.645.
I think it's
Plus or minus, either way. Let's just hang on both sides for the moment.
Yes, 645.
Good. Okay, now, instead of saying that we have a 68% confidence that the population mean is one standard deviation from our sample, we can equally well say we have a 90% confidence that the population mean is 1.65 standard deviations from our sample, true?
Yes.
And we could also go to 95%. And if we go to 95%, then what's the z-score?
2575.
So that we can say,
It's a 95, no, excuse me, 1.96. Apologize.
so that we can say, we have a 95% confidence that the difference between the mean of the population and the result of our one sample is less than 1.96 sigma. We have a 95% confidence of that, agreed? So now we have established the different amounts of confidence that you can have, agreed? Now, the only thing that we have to now look is, when are you going to choose to reject, and when are you going to choose to fail to reject? Okay? Now, if your one sample falls in this region, that supports the fact that the difference between your sample and the center is less than one standard deviation. If your sample falls in this region, that supports the fact that the difference between your sample and the center of that graph is 1.645, agreed? Because that is where your sample fell in the distribution. Now we can do this hypothetically without even knowing the actual center, because all we're doing is saying how far from the center we are. Without necessarily, we don't need to know what it was. Now, if we are going to turn this around now, we can say that I'm going to take one sample. And if the one sample does not fall in the 1 sigma area, then I'm going to reject the null hypothesis. Because I can say, if my one sample falls out here, it's not in the 1 sigma area, is it? So that means something is wrong. That means that the center of the graph might not be here, because here is too far from my sample, agreed? So that means I can now conclude this is not the real center. Because if this is the real center, my sample is too far from it. So I'm going to reject the hypothesis that this is the real center. Now, if I got a sample that was very close to this hypothetical center, that would tend to support it, would it not? If I got a sample that's very far away, then it would tend to not support it. So the farther away from the hypothetical center your sample is, the less support it's given that that indeed is the center. And remember, we don't really know that this is a center. It's somebody's guess. And what we're doing is trying to establish the confidence that we might have that that is the center. If you take a test and it comes very close to your hypothetical value, that tends to support the fact that your hypothetical value is indeed the center. But if you take a test and it comes way out here, what's the probability that you would get a test way out here if indeed this was the center? How often do you get tests way out here?
Not very often.
Not very often, agreed? So you say, well, if this is the center, I would not get this test result very often, so I'm going to decide that it's not the center. The center is someplace else. The center is someplace closer to my test result. The center is not so far away, because it's not likely that I would have gotten that result.
So ultimately, we're trying to say, is my test result and my center truly lining up with each other, or is my center and my test result not lining up?
That's exactly what you're trying to say. And by lining up with each other, you mean lining up with each other
Being close
how
to-
far?
Yeah, like, are they close together or are they far apart?
Exactly. Now, at some point between close together and far apart, you're going to cross the line where it's no longer believable to you that that is the center. They're too far apart, agree? And that's called Z-critical. And that comes from your confidence level. If you want a 95% confidence level, then that transcribes into a Z-score of 1.96, agreed? So you go out here and you measure 1.96. And if your test comes on the right side of that, you're too far away. So you see, your confidence level gives you the maximum Z-score that you can have and still support the hypothesis. If your Z-score exceeds Z-critical, then you reject that this is the center. You're too far away from it. So your confidence level gives you the maximum Z-score that you can have and still believe that that is the center. Now, if you have a higher confidence level, then if you have a higher confidence level, then you must go further away, agreed? You must go further away for a higher confidence level. And so these are a matched pair. If you want a high confidence level, then you must be very far away before you choose to reject it. If you want a low confidence level, then you can be fairly close to it and reject it with a low confidence level, because you could be wrong. Now, what would it mean if you could be wrong? It means that indeed this was the center. And this sample will actually be found a small number of times, even if this is the center. This is not zero, is it? You will get it a few times. And just maybe, your sample was one of those legitimate times. Meaning that you're making a mistake to reject this. But you say, I'm willing to take that chance, because I'm only declaring a 95% confidence. So I admit that 5% of the time, I will be wrong to reject this. Because 5% of the time, this extreme result would have occurred naturally. And I'm making a mistake to reject it. So the logic behind hypothesis testing is you establish the maximum distance from the center that your test result can be, and still have you supporting the thesis that this is the center. Once you establish that before you even test, going in, once you establish the maximum distance that you can have and still support that this is the center, then you take a test. And if your test is outside of your maximum distance, then you withdraw support that this is the center. Admitting that you could be making a mistake, but you have to do it because it's more likely that this is not the center in that case. Now, you never do know what the center is because this is hypothetical. All you know is that you either reject or fail to reject the hypothetical center that somebody has proposed. Somebody proposes a hypothetical center for the population, which is also the center for all of your sample means, and you are either going to be close enough to that or not close enough to that, and if you're not close enough to it, then you reject the suggestion that that is the center.
So here we are, the author says, my hypothetical center is here.
Yes.
And he says, with a 95% confidence level, so 95% of the time, your one sample is really going to be that close to what I'm proposing.
1.96 sigma.
And 5% of the time, it's not going to be as close
It's
to my
not.
hypothetical, my proposed center.
Absolutely right.
And when that 5% happens, you reject the,
What is it you reject? You reject the thing that you mentioned first. You
center.
reject that your proposed center is the center.
Rejecting the center.
You reject the proposal that that is the center.
95% of the time, we're failed to reject that. Well,
That's right.
I'm gonna say this is blasphemy, I got it, but just from thinking, we're saying 95% of the time we would accept, and I understand that.
No, it's cool, it's cool.
95% of the time, we're accepting that this is the center, and
Yeah.
5% of the time, we're not accepting. this is the
Exactly,
center.
exactly. Exactly.
So you want us to express that by just writing reject or?
Well, in a simple language, you express this by either writing reject or fail to reject. But in order to satisfy the lawyers, you have to go back to that little flow chart and get the legal correct language. But all you are doing is rejecting or failing to reject. Now, let me give you a real-life example that's close and dear to your hearts, agreed? If I tell you, if I suggest to you, hypothesis, 20% of the population of Kadena Air Base smokes. That's my hypothesis, agreed?
Right.
Now, the next 5 people that come through that door are going to be a random representation of Kadena Air Base, agreed? Now, if 1, 2, 3, 4, 5, all 5 of them smoke, 5 out of 5, random, do you any longer believe my suggestion that 20% of the entire population smokes?
I mean, if it was simple random, then I would say that I would reject that it was 20%.
Right, because that's an extreme situation, isn't it?
We got 100% that smoke.
That's right, in our sample. Our sample is so far off from our suggestion, true?
Yes.
Now, on the other hand, if out of the 5 that walked in, 2 of them smoked, that's failed to reject, right?
Yeah,
That could easily happen, true?
Yeah.
Right, so there's some cutoff point that we decide. And what we're gonna decide is 60%, which means 3 of them agree. So the next 5 walk in, and if 4 of them smoke, then we reject the 20% agree. And if 2, 1, 2, or 3 of them smoke, we fail to reject. So we establish a cutoff point in which our sample causes us to no longer support our suggestion, our one sample. So we were looking at a 60% confidence level, agreed? So if 3 out of the 5 smoke, that's not extreme enough to reject. The base-wide percentage is 20. But if we get 4 out of those 5 smoked, we've decided that's sufficient.
Maybe at this time, the actual base smoking is probably more like 30%.
That's right. That's what we're concluding, that our hypothesis should be rejected. But it is possible that it is true that 20% of the base smoke, and we just had a freak set of 5, true? So we could be making an error. But we accept that. We accept that risk.
That makes a lot more sense now. Let's just figure out how to pull the information out of the problems.
Exactly. Exactly.
So this. All right, so.
No. Type 1 error and type 2 error, I do not get that,
Okay, you do. You just don't know that you do.
probably.
This is just what we said. We said that if 4 of them out of the 5 smoked, then we were going to reject the hypothesis that 20% of the base smoked, agreed? But then we said we could be making a mistake. It could be true that 20% of the whole base smokes, and we just got an unusual set of 5 people, true? So that means we could have been making an error. So we could have rejected the base-wide population of 20%, when in fact the base-wide population of 20% in fact is true. And that's a type 1 error. When our sample is in the reject zone, we decided to reject 4 or 5 smokers, true? We got 4 or 5 smokers, so we rejected, but we were wrong to reject. That was just an unusual set of 5 people, a freak sample that came in. So that's a type 1 error. When our sample causes us to reject the null hypothesis, when in fact the null hypothesis is true. Okay. Now a type 2 error is even easier. Suppose those 5 people walk in the door and only 1 of them smokes. Then do we reject the hypothesis that 20% of the base smokes?
Is that
Fail to reject. But if in fact that 20% is a wrong number, then we should have rejected it, agreed? But our sample forced us to fail to reject a null hypothesis that was in fact wrong. And that's a type 2 error. The null hypothesis is in fact wrong, but our sample was free. Our sample seemed to indicate that the null hypothesis was right, so we failed to support it. But then if we actually uncover the bedclothes and see what the real base population is, we find out it's really not 20%, but our sample misled us. And that's a type 2 error. When you fail to reject the null hypothesis, when in fact the null hypothesis is wrong, you're guilty of a type 2 error, right? So if you have children, true, and suppose you're not sure if your child is lying to you, okay? And so if you decide Okay, well, I'm not gonna call him out. The evidence isn't strong enough. So I'm not going to accuse him of lying. The next day you find out he did lie, right? That's a type 2 error, agreed? Now, what's a type 1 error? He comes in, gives you some story, and you say, you're lying, go to your room. Next day you find out he wasn't lying, right? Type 1 error.
Done that a couple times.
On which end of it? Both ends?
Yeah, really, both of them. I got one that's daggone won't lie to you to say, yeah, straight as an arrow, and I got one that's like, I don't know what happened there.
So those are type 1, type 2 errors, which I think you know. Yeah, we'll give you an example with numbers. Same with these numbers right here. We're going to establish our red zone with to be a z-score that corresponds to occurring 95% of the time, agreed? So we establish our red zone based on the confidence level that we choose, which gives us the partner z-score. Now, if we take one sample and we are examining whether this is indeed the center, if indeed this is the center, then all of these scores under the curve could happen, even with this being the center, true? Now the scores close to the center are more likely to happen, true? These scores are less likely to happen, and these scores are even less likely to happen, but they could still happen with this being the center, agreed? So what's the probability of this score happening if this was the center? It's 5%. True? Because this is the z-score for 95% and 5%. So 5% of the time, you would have gotten a sample over here with this still actually being the center. It would have occurred naturally. But if you've decided to reject that, that means that 5% of the time, you're going to be rejecting centers that are actually true. Because when the center is true, you will get results out here 5% of the time. Now that means on the average, you're going to be guilty of a type 1 error 5% of the time. When you reject at this point, 5% of the time, you are going to reject null hypotheses that are in fact true. Predictably, you're going to be wrong 5% of the time. If you decide, going by the facial expressions of your child, you say, okay, if his eyes are both wide open and his mouth looks like an S and his nose is dribbling, then I'm going to say that he's lying, agreed? Because those are extreme symptoms to see, true? But, and you say, in the past, most of the time when he does that, he is lying, true? But even when he's not lying, that happens 5% of the time. So if you, every time you see that, you say he's lying, you're going to be wrong 5% of the time, true? It just naturally occurs. And so that's called the percent of type 1 error, is the difference between your confidence level and 100. Gives you the percent of time you're going to be wrong. If your child gets those funny expressions 95% of the time when he lies, and 5% of the time when he tells the truth, and you accuse him of lying every time he looks like that, then what percent of the time are you going to be wrong? 5%. So that's how you calculate the value of a type 1 error, the actual number. Look, every time a guy looks like that, that's lying.
I just have a loss, so.
This is conceptual. conceptual stuff, it's abstract.
Okay, so here's one that I'm kind of making mistakes with. This was more in the calculations, when we're talking p-value, and we're talking, which probability, p-value, p success, q failure. Like, I thought that when you're talking p and q, success versus failure, that we were talking the probability of this happening versus the probability of that happening.
Yep.
But then we turn around and use P is the proportion, which to me, I thought that was also saying probability of this happening versus the
That's
probability
true.
of that.
That's true, and,
But we're using them very differently when we're talking about.
yes, they're using very differently, they're measuring very different things. And, does the book use capital P in one case and small p in the other? That would at least help a little bit.
I mean, it is saying capital P for, and then dash value.
Yeah, capital P for the p-value, agreed? Okay.
Is that
So-
how we use p hat?
Pardon me, p hat is a small p, isn't it?
Small
Right, and capital P
for the
Population.
is, capital P is not for the population, it stands for something else. So first I'll tell you what capital P stands for. Now here, we're testing a mean, true? We're not testing a proportion. So there's no small p anywhere in this problem. There's no small p, which is a proportion of the population. There's no small p hat, which is the proportion of your sample, because we're not testing proportion. We're testing what? Mean, agreed? We're testing a mean. So there's no small p's here in this whole board. Is that clear? Small p's stand for proportion. However, there is a capital P. And to find out the capital P, you first have to find your mean value of your sample, agreed? Now, the mean value of your sample has a z-test that goes with it, doesn't it? Your mean value of your sample has a z-value, doesn't it? Your sample mean has a z-value. So let's find that z-value on the graph, and I just did. Now, you notice that your z-test is on the left side of z-critical, agreed? That means fail to reject, doesn't it? Good. But another way you can decide to fail to reject is not by comparing this z-test to z-critical, but by comparing its partner. What's the probability of z-test compared to the probability of critical? Is the green larger than the red?
Yes.
Yes. That means that it's not sufficiently improbable that your test occurred. Because your red zone says if your test occurred with less than 5% probability, I'm going to reject the hypothesis. But your test occurred with 7% probability. That's not improbable enough. Because what you're going to do is reject the null hypothesis if your test value is sufficiently improbable, true? If it's so far to the right that it has little likelihood of being natural, it's improbable. If this is. So what is the threshold of improbability? The 5% is your threshold of improbability. Because you're saying that if the probability of my test result is less than 5%, then I am in the reject zone. And if you're in the reject zone, then the probability of your sample is less than 5%, then you reject the null hypothesis. Suppose that we did not get a z-test here. Suppose we got a z-test down there. Is it very likely that we would have gotten a z-test down here? No. So what's the probability of getting a z-test down there or greater is the area to the right, isn't it?
You say greater, you mean, what's the probability of that z-test or another one that's even more extreme? than
Even
that?
worse, exactly.
Okay.
That or even worse is represented by the area to the right of that. Read? So if we look up the area to the right of that, then that's a probability of getting this z-test or worse if this is the center. And that probability is lower than what we were willing to tolerate. We were willing to tolerate a 5% probability of getting a z-test that was this much or worse, but we got a 1% probability. That's lower than our threshold, okay? And we do the same thing with the smoker walking through the door. Let's do it in terms of probability. We're going to establish a cutoff probability, agreed? So we're going to say, now these are, let's say, proportions. It doesn't change it. We're saying that if 3 out of 5 people smoke, then we're going to fail to reject, agreed? And if 4 out of 5 smoke, we're going to reject. If 5 out of 5 smoke, we're going to reject. So now, that means that we have a 60% confidence level, agreed? 60%? So that now, so what is the size of the reject zone? Is 40%, agreed?
Yes.
40%, okay? Now, if 4 of those 5 are smokers, then what's the probability of that occurring? Let's say only 20%, agreed? 20% of the time that will naturally occur. But is that 20% less than our 40% that we're willing to accept? Yes. So if P is low, the null must go. So P was lower than our threshold P, agreed? The p-value comes with your z-test, capital P. And it comes with your z-test by looking it up in the table. And if that's lower than the threshold that you're willing to accept, then you must reject the null hypothesis. So if we got a 20% possibility of that sample occurring, and we said if we get less than 40, we're going to reject, agreed? Now, if 3 people come through the door that are smoking, then that's going to occur 60% of the time, which is greater than our 40% cutoff point, agreed? That's going to occur naturally, so we have to fail to reject. So you can reach the same conclusion by either comparing your z-test to the z-critical, or comparing the probability of your z-test with the probability of your z-critical. So that's what the capital P means. The capital P is you take your z-test and you look up its probability in the table. That is what capital P is. It's a table lookup of your z-test. It's got nothing to do with small p or small p hat. All of those are you use to evaluate your z-test in case you're using proportions. So if you're using proportions for your problem instead of means, then you evaluate your z-test by z-test equals the proportion that you found in your sample, agreed? Minus the suggested proportion for the population. Now, in our case, we might have found a 60% proportion in the sample, 3 out of 5 that walked in, agreed?
Right.
Now, the suggested proportion for the population is 0.2, isn't it? So this would be 0.6 and this would be 0.2. So that's what these proportions mean. Now, at the bottom, we have the square root of PQ over N. Now, the size of our sample was 5, true?
Right.
Now, the probability of the population was 0.2. So what is the Q for the population? 0.8. So you see, we put all these numbers together and we get our z-test. Once you get your z-test, you look it up in the table and you get a capital P for your z-test.
That makes more sense now. Because we're saying our suggested population percentages, that's where that rolls into our success and failure.
Yes,
PQ.
yes.
Whereas our proportion, which is also the probability of success and failure, but it's for our sample.
Nice. Nice. You got it.
Does that make any sense to y'all?
Yes.
Yeah.
That's fine.
It's time for a concrete problem.
Okay.
Pick a concrete proportion problem and let's go through all these steps. 434, I think, is the page in question. 435, 436, and 7 is full of them. Almost any one of them.
All right, let's start easy and go, we'll build up from there. Like, number 9 is our beginning. Let's try that out.
Let's read the directions. Oh yes, test the claims about proportions. Test the given claim, identify the null hypothesis, alternate hypothesis, and test statistic. Capital P-value, right, which is the probability of the test statistic, table lookup. And critical value is the alpha. If you have 95% confidence level, your critical value is 5%. And that 5% also has a z-critical, doesn't it? That you can look up in the table. So that's how we get all of the numbers and say use the p-value method unless your instructor specifies otherwise. So we are ready to begin this problem. In a Pew Research Center poll of 745 randomly selected adults, 589 said it is morally wrong to not report all income on tax return. Use a 0.01 significant level to test the claim that 75% of adults say that it is morally wrong to not report all income on tax returns. So let's try to get a picture of this before we write anything down or start throwing equations on the board. What is the suggested proportion of the population? What is the suggestion? We suggested that 20% of Kadena Air Base smokes. What are they suggesting here?
75.
75%, agreed? So that's our P. So suggested.
That's our lowercase p.
Yeah, it's lowercase.
Okay.
Right. So suggested population proportion P of 0.75. So we've established that, true? Okay, now, what is the confidence level? What is the confidence level that they want to declare their result with? That's the alpha. What's the confidence level?
99%.
99, so it's a 99% confidence level, agreed? So confidence level is equal to 0.99, which means that alpha is equal to 0.01. Now they're going to conduct a sample, true? So they do one sample test. Now what was the size of the sample? Sorry?
745.
Done right. Now what proportion of the sample, which is known as p hat, what was the proportion of the sample that were saying it was morally wrong?
589.
589 over 745, agreed? Okay, now what we're going to do is write down the claim. Now the claim might be an equal sign, it might be a greater than or an equal, or just a greater than, or a less than, or less than or equal. There are 5 choices for the claim. So what is the claim? It's equal to 75, agreed? So the claim is that the population mean is equal to 0.75. Now that means if our test result is up around 96%, that's not likely, is it? No, it's not likely that the population mean is 75 if we get a test result up around 90, true? 90 would not be likely. Also, if we get a test result down around 7%, is 0.75 likely for the population? No. So if our test result is either too high or too low, we're going to fail to we're going to reject that, agreed? Because they're saying it is 75. And if we get a 5% result, then it's not close enough to 75. If we get a 95% result, it's not close enough to 75, true? So what we're going to do is have a two-tailed test, true? And if our sample is in the left reject zone, we're going to reject. If it's in the right reject zone, we're going to reject, agreed? So the anti-claim is that P is unequal to 0.75, true?
Yes.
Now H0 is the one with the equal sign, which says P equals 0.75, and H1 is the other one, is that P is unequal to 0.75. So the first thing that we have to do is we have to draw our graph.
HO would be our, H0 would be our null.
This is the null hypothesis. H0 is the null hypothesis. That's the symbol for it. Okay? Now, what we are going to compare is, well, this curve that I've drawn is the results of taking an infinite number of samples, all of size 745, true? All of size 745. And that infinite set of samples would have some mean value, true? And our mean value for all of the p-hats is also going to be equal to the population proportion, because we established that the mean of an infinite set of proportion samples is the same as the population, because that's true for the mean, for the proportion, and the variance. The center of the sample distribution is the same as the center of the population. So what we want to do is test whether this is indeed equal to 0.75 by taking one sample. Now, if our sample is way up here, it's time to reject, agreed? Because it won't be likely. If it's way down here, it's time to reject. So how far is way up there? Well, the probability of this reject zone is the area under it, isn't it? The probability of getting a result that is either, has this z-value or higher, is the amount of area. And similarly, the probability of getting this z result or lower is this area, true? So these two areas add up to the probability of rejecting it. And what was the probability of rejecting it? 1.01. So we have to divide that into two pieces. So how big is this piece? 0.005. And this piece is also 0.005. So our test statistic of the z-value z-test, when we find it, when we look it up in the table, it's going to have a capital P-value, isn't it? Now, if the capital P-value is in our reject zone, then we reject, agreed? If the capital P-value is in this reject zone, we reject. But if the capital P-value is in our fail to reject zone, then we fail to reject. So we have to find capital P. Now, capital P is the partner of z-test. Because every z-score has an accompanying probability, true? So let's find our z-test, which is equal to p hat minus p over the square root of pq over n. Now, p hat is that fraction. What is that fraction?
0.7906.
0.79. So this is equal to 0.79 minus p. What was p? 0.75. And in the bottom, we have the square root of 0.75 times what? 0.25 divided by?
745.
Good. Now, this is what you've been screaming for 7 weeks. It's just give me a numerical calculation that I can plug in. And here it is. So you have to find out what is z-test. Sorry? 2.52. Now, capital P, so 2.52, now that's a positive number, isn't it?
Capital P is P-value.
Sure. Oh, sorry. Okay, 5 minutes, I'll say, yeah. Now, let's eyeball, where does a z-value of 2.52 come? It's a positive z, isn't it? So it's going to be on the right side someplace. So it could be here, or here, or here. We don't know where. It's somewhere over there, agreed? So once we find it, we have to calculate its probability. And if its probability is smaller than the red probability, we reject it, agreed? But if its probability is bigger than the red probability, we fail to reject it. So please tell me the p that goes with 2.52. And remember, we're going to be on the right-hand side, so you have to subtract it from 1, right? Point 0059. Very touchy, agreed? So it's right here, isn't it? It's almost as small as the red zone, but it's not quite, is it? Now, since it's not quite as small as the red zone, then what is it that you must do? Reject or fail to reject? Fail to reject. So we have made our conclusion that we fail to reject. We're doing number 9 on page 435. Okay? Now, we have failed to reject it, agreed? But that's not going to stand up in court, because the judge doesn't know anything about null hypothesis. All the judge knows is that somebody made a claim. So you have to state your conclusion not in terms of the null hypothesis, But you have to go back to the original claim and state your conclusion in terms of the original claim. All of this was so that you could find the right conclusion in terms of the original claim. So what was the original claim? That the P of the population was equal to 0.75, agree? So this was the claim. So now we go to that legalese flow chart. What's the page? 417. So Joey, lead us through this flow chart.
So does the original plan contain the condition of equality? Yes.
Good.
Do you reject the, no, or H0? No.
We did not, agreed? So now this is the way you state your conclusion. Read it to us.
There is not sufficient evidence to warrant the rejection of the claim that P is equal to 0.75.
Right.
That's all we have to do.
And done. There's not sufficient evidence to warrant rejection of the claim. That will stand up in court. The second, let this sink in, agreed? So, because our test result was in the acceptable zone, we could not reject it. So there's not sufficient evidence to reject it. It's inconclusive. It still could be wrong, but based on this sample, we can't say it's wrong. Not yet.
Is there any such thing as it's getting too close, like maybe one?
Oh, well, that's a personal call. If you want to fudge the numbers a little bit, you can always do that. And what makes too close is entirely up to you. Everybody agrees on what is not close. But when it starts getting close, it's individual judgment. Okay, now I have to set up a makeup test. So let me take a test into another person. I'll come back, we'll pick up your question as soon as I come back. Feel better?
Yep. Lots.
First time. So you want to take it in a noisy room? Okay.
Long nights, friends, sick.
So just dump some books and stuff over there and have a nice test. If we get too noisy, just take it out to a quiet place.
It's an emergency.
What you just said, inpatient. I thought the same, I was like, oh,
She was in a regular, well, she lost a baby. Yeah, so I was there with her, so I was taking me a nap, and I wasn't planning on, I was sleeping. Yeah.
Who lost the baby?
A friend of mine, she had to deliver it, so I was in the delivery room, so her delivering the.
Was it that
stillborn
E
baby.
thing in Encapsula or something?
No, she went in for a regular routine to find out the sex. She was 16 weeks and the heart wasn't beating.
And the heart wasn't beating, it had never been beating?
It had been. She had just got a cerclage, a stitch put in her cervix a couple of weeks ago.
She just had what?
Cerclage, a stitch put in your cervix to help your cervix not open, dilate on its own. I had that too with both of my kids. They put a stitch in your cervix and it helps your cervix.
So that happened about the same time the heart stopped beating? Coincidence or causality?
No, the heart was beating still then.
After that?
After that, yeah,
Okay. So then she just went in for a routine checkup and it wasn't beating?
and it wasn't beating.
So what did they do, C-section, yank it out?
No, they induced her labor.
Induced the labor and it came out?
Mhm.
So I have to scrape and all that?
They haven't scraped yet,
Going to?
they didn't say, I had to talk to her,
Yeah.
they didn't say. Cause they pulled out the placenta.
Oh, I bet she's disconsolate, I mean,
Yeah,
totally depressed, sad, off
Yeah.
the scale. I can't imagine. First child?
no, it's her third time having a miscarriage, but they have one child after the first two.
So anyway, they have one.
They have one.
Okay, let's get back to this. You had a question?
Yeah, I did. I was wanting to ask, because when I was reading this the other day, I didn't really fully understand, but when it, I guess I should have, but when it says the equality part, I noticed on this one is the equal sign, so that's what I need to be, that's what it's saying, that it equal the claim.
Right, the original claim contains the condition of equality. Now, let me give you some tests. P is at least 0.6, that's a claim. Does this claim contain the condition of equality?
No, because it says at least 6.
I think that P being at least means this.
Yes.
It includes 0.6, doesn't it?
Because it has the equal.
Is that an equal sign? So the
Yes, sir.
answer is yes, it
Okay.
does.
So if it has the equal in it,
These are the conditions of equality, any one of those three,
okay.
then it contains the condition of equality.
So if
In the
it was
original
just
plan.
less than or more than,
Right.
then.
And it doesn't.
Okay.
So if you say mu is less than 3 pounds, if this is the claim, does this contain the condition of equality?
No.
No, it doesn't.
Okay.
Right.
Okay, that makes sense. I was understanding how to work the problem, I just wasn't understanding how we were getting
Mhm.
the decision to fail to reject or the reject part.
Mhm.
That's what wasn't making sense.
Okay.
Okay. That clears up the whole thing.
So we just did one example, soup to nuts, the whole thing, and people are absorbing that at the moment. That's what's going on. Now, while Kevin absorbs that, you guys can ask for something more if you want.
I didn't understand chapter 10 at all.
At all.
I just remember Y, MX plus B or something.
Well, that's a small part of it. The major part of it, and as far as understanding goes, is that you are comparing two parameters to each other. Two parameters, agreed? Now, I made a sample case. One parameter was the speed that you drive, and the other parameter was just braking distance. So we can make a set of data points, like you drive 30 miles an hour and your braking distance is 40 feet. That's one data point. We measured it, right? Another data point might be that you drive 60 miles an hour and your braking distance is 100 feet, true? So a data point consists of one speed and one stopping distance. So now we ask the question is, are your stopping distances correlated with your speeds? Are they correlated with your speeds? In other words, if your speed goes up, can you predict what your stopping distance is going to do? Can you? Yeah, you can. That means that they have some correlation, agreed? Now, would your prediction be that your stopping distance also goes up? That means it has some positive correlation. Now, let's take a different study. Suppose we compared your speed with your miles per gallon, right? So we take some data points. Suppose you drive an average speed of 40, and your miles per gallon is 20, right? Now I suppose you drive an average speed of 60, and your miles per gallon is 15. So you see we get some data points. So one data point is the average speed you drive, and the miles per gallon. So we can make a 2-column list of data points, can't we? All the speeds and all their partners, miles per gallons. Now, would you predict that these two parameters are correlated?
They get it.
Well, first you would. That if you know one, you can predict the other, agreed?
Mhm.
Right. Now, in order to predict them, you need to have an equation. Suppose I tell you y equals 2x plus 3. That's prediction, because if I tell you an x, such as your speed, then you can predict your stopping distance from this equation, can't you? So this is where y equals mx plus b comes in. What we do is we take all your data points and we use them to construct an equation that describes, on the average, just how y goes up when x goes up. And we can use this line to measure your stopping distance at speeds that we didn't actually measure. We can use it to predict other speeds from. So in order to generate this line, in general, it will be of the form y equals mx plus b, agreed? So if you have your two columns of data, then you can take your two columns of data and use the two columns of data to calculate an m from the two columns of data, right? And this is the equation that you use to calculate your m. It is on page 555. Now, instead of M and B, Triola uses B1x plus B0. So that's just a change of symbol, agreed? So if we want to calculate the slope in Triola, we need to calculate B1. Now, remember, what we have are two columns of data. We have a column of x values, let's say some speeds, 40, 50, 30, and 80. And what we have are some y values, which are their stopping distances. Suppose this is a stopping distance of 60, 70, and 40, and 90. So these are x-y pairs, aren't they? So now what do we need in order to use this equation? We need the sum of x. Do you see the sum of x?
All things together.
So we just add those up. And we need the sum of y. So you just add those up. No, don't worry about it, just so you know how to do it. I mean, I know you know how to do that. You don't have to prove that to me. Okay, now we need another column called x times y. So let's generate that column. 2400, 3500, 1200, and 7200. X times y, okay? Now we also need the sum of x times y equals. Now if you look at this equation for B1, can you tell me any other columns that we need? X squared. So let's do an x squared column. 1600, 2500, 900, and 6400. And we need a sum of x squared as well, don't we? Hmm?
Y squared.
I don't see any y squared. Do you see y
She
squared?
said, why do we x squared?
Oh, no, I thought, I was thinking from.
What, are you
class,
on the
I was
page?
thinking of Y.
The page 555?
No.
Well, go there.
Sorry. So, for, he says solve for B1, so we have to get the sum of x, y, the sum of x, the sum of y, and we can multiply that sum of x squared, and then minus 15 sum of x squared.
Yeah, I was just saying Y squared, because I thought that's what we did the last time, but I might have.
We might have done that because we're doing something different.
Yeah.
For this one, you don't need the y squared. However, yeah, you don't need the y squared for this one. So we can calculate the slope using this equation, true? Now, can you also calculate B0 using the equation next to it?
Yes.
And that means that you will have your prediction line, y hat equals B0 plus B1x. And it might come out to be like this. Y hat equals 42 plus 13 times x. Okay? Now, you can use this to find your stopping distance for some other speed that's not in the equation, once you have this line. And the name of this line is called the regression line. That's just its name. Okay. So that's how you start with a table of data, x, y points, and you calculate the slope and intercept for the line of best fit, called the regression line. Yeah, this is just punch in. That's all it is.
Redoing that.
What are these problems? Hello.
Hi.
Hi. Did you just want to say hello?
No.
I'm glad you came by.
No, actually, I'm gonna take my test.
And you're test number 2, agreed? Okay, so I'm gonna have to go out to the car. Let me give these guys their problem, and then I'll go out to the car and get your test 2 things. Why don't you go get it?
Alright, it's parked inside the building. License plate,
Okay,
camera.
good. Now, let's go to page 569, and I want to do number 17.
Big numbers.
No, I picked the smallest numbers. If you can find one with easier numbers, then we'll do that one. But this seems to have the easiest numbers. How about 15? Maybe those are easier. Okay, do 15. So now, one of these columns is X and one is Y. It doesn't matter which, agreed? So I want you to find your B0 and your B1. And after you find them, then you've got your equation, agreed? Once you find your equation, then you predict the value for X equals 100. So you let the right arm equal X, okay? Right arm equals X, left arm equals Y. Because we're biased against left-handed people, that's true. Is this room too noisy for you to test in?
Just a little bit.
Okay, have a seat while I get the test, we'll find it quiet. table your stuff right here. Just bring it in so you need.
Yeah, he is. I bet you he is. He's out of stock.
No,
Hopefully
it's
you
like
only
the
have
last
one. Yeah, maybe I have only one of these. Because this is a long process.
Wow.
I just want to hear.
Gosh, he's
Close, close. So it would number 11,
Page.
434. Alright, so understand.
Let me cut you up just a second.
Subtract expert points.
Well, I think,
It is expert.
what is the, yes, the sum of x and then the x
X squared.
x squared. And then you have to, yeah, x squared squared. I mean, x, sum of x squared, and then, yeah, it shows it get tongue tied. Yes, but I know. Oh, damn, it should do. 455 squared.
I'm not there yet, go down.
Um, Okay, this is good, and there's more. No,
Well,
you're
and
perfect
that's-
so far.
And that's where my, now I'm at the hang-up point. So determining my z-test, my z-critical was .01. So that's my reject, this is my reject zone. On that side,
And the size of that's .01.
yes.
And
My
this is,
z-test came in
not this is z-test, this is your P
Yes,
of your
x,
z-test, right?
the
Your
sum of
z-test
x,
was
and then
3.48.
square the sum of x, so square the 455.
X squared is X squared.
No, this is a probability of your z-test, .003. So if your z-test is 3.48, okay? Now, usually, where does z-tests come in? When they're around 3. This is around 1, right? Round 2? Where do 3s usually come in?
You get 1.7.
Yeah.
Which one you doing?
So where's your test? Give me a nice export legitimate. It's way out here. So put it right here, just so it doesn't draw. Now, it has a probability, so shade the area to the right. And the size of that is .003, right? .0003. Right. And your reject is anything less than .01.
Did you do the?
Is this less than .01? So you've been rejected the null hypothesis.
I wrote the second part down while I wrote the last one. Okay, I got B0, right?
That's it.
Now, that's got nothing to do with the claim, you're just rejecting the null hypothesis. But the null hypothesis was the anti-claim, agreed?
Yes.
That means that you support the claim. So you have to get the language right now. So go to your language page and, yeah, and get your claim right.
Still on P1.
Oh, yeah, 'cause you gotta redo it, right? You have to
Did they
redo
budget
it.
in one? I swear I budget, right? I think like 31 trillion.
No, why do you think?
Why did you have to get that?
Multiply.
Are you writing down all your steps?
That they like it how it looks.
I put in the calculator.
Could you read your final conclusion to me in words?
Sample data supports the claim that successful challenges are greater than 1/3.
Yeah, well done.
I don't know what you're doing.
And it does, doesn't it?
All right, do one more. Let's see
I
what we-
still didn't use that into my calculator.
I don't know why it's giving you something different.
You know how much in my calculator? Let's see what I can pull.
Okay, did you get your B0 and B1?
Yes, sir.